The purpose of this video is to prepare you for the homework in section 3.9. In its simplest form, this is simply an assignment on finding tangent lines, but they're going to use some new vocabulary, and that new vocabulary is where they talk about local linearization. And a local linearization means we're taking some curve like the one shown right here, and we're converting it to a line because lines are easier to work with. And it's good for approximation in that local area. And when we're talking about local, we're talking about an area that is near the point of tangency. So if you're near the point of tangency, you can see that this line is very near the curve, and so we have linearized the line on the curve and can use a line to approximate values. Now once I get out here, we can see that the line and the curve aren't near each other, so it would be ridiculous to use the line to estimate out here or even out here. It is only good in this local area. All right, so let's look at our first problem. We're given a function and we're asked to find the tangent line approximation near x equals 4. This is basically saying find the tangent line at x equals 4. So let's go ahead and do the work for this. We know that we first need a point, so let's put 4 into f. So f of 4, see I've got 4 squared is 16, 4 times 4 is 16 plus 1, it looks like my y value is 33. So I have the point 4, 33. And now I need the slope, so I'm going to find the derivative. F prime of x equals 2x plus 4, and f prime at 4 therefore equals, looks like 8 plus 4, or 12. So our tangent line is going to be y minus 33 equals 12, x minus 4. And what use is that? Well, it's good to estimate things like 4.1. I would not enjoy figuring out 4.1 squared plus 4 times 4.1 plus 1, but I could use the tangent line to get a pretty good approximation. So let's give this a go. 12 times 4.1 minus 4, and I get y minus 33. I get 12 times 0.1, which is just 1.2, and y equals 34.2. All right, so then let's just check and make sure this makes sense. So let's pull out our calculator here, and I'm going to go ahead and put that original function in. So let's do that over here. So y equals, I've got x squared plus 4x plus 1. And I can find values by doing vars, y vars, function y1, and I want to do this at 4.1. And there's the value, 34.21, my approximation 34.2. We can see, wow, that is a pretty good estimate. Now, let's just compare if I go further out what happens. So let's do the same thing again, but let's say do 4.5. So that's the actual value, and then I could do 33, I'm using my tangent line here, plus 12, parentheses, 4.5 minus 4, and you're going to see it's still close, but not nearly as close. Now I'm off by 0.25. Before I was only off by 0.01. So you can see the farther I go from that tangent line, the less accurate my approximation. Okay, last question. Is this an over or underestimate? Well, we should immediately recognize that, wait a second, this is a parabola. Not only is it a parabola, it opens up. And parabolas that open up are always concave up. So always concave up. And if you're concave up, where's your tangent line? Your tangent line is sitting down here below, and therefore we can see that this is going to be an underestimate. Okay, and it's an underestimate because the curve is concave up. And if we go back to our calculator here, recall that when we did this first estimate, we did 34.2. The actual was 34.21. So you'll notice this was an underestimate. It was less than the actual value. All right, so now let's just do this in general. What we're doing is taking a curve called f of x. On that curve there is a point. I'm going to call the first, the x-coordinate a. That means the y-coordinate is f of a. And then the slope, therefore, would be f prime at a. So when we write our tangent line, we've got y minus our y-coordinate, f of a, equals our slope, f prime of a, times x minus a over here, which is our x-coordinate. And then we are going to, in this linearization, often say f of x is approximately. Now remember, f of x is the actual function, all right? And we're going to solve this thing. So y can be rewritten as f of x. This f of a has to go to the other side. F of a plus f prime of a x minus a. And this is true that it's approximately equal for x near a. And remember, when we're talking about being near a, then this is back to where we're talking about values that are near that point. All right, so let's we've got this big one here. This talks about if we're differentiable, then for values near a, the tangent line approximation is this. This is what we just wrote on the previous screen. All right, so we're going to use that now. Right here, we're asked for the local linearization of sine x near x equals pi. So students look at this and they go, ah! But if we recognize right away, local linearization is just another way of saying tangent line. Tangent line. So let's go for our tangent line. Let's start by just naming our function. We can let f of x equal sine x. So let's figure out f of pi. That's going to be sine pi, which is going to be 0. That means that we have the point pi 0. There's our point. Now, f prime of x equals cosine x. F prime at pi equals cosine pi. Cosine of pi is -1. There's my slope. So what's my local linearization? Y minus my y-coordinate, which is 0, equals my slope, -1, x minus my x-coordinate, which is pi. And I can simplify this one, -x plus pi. And just maybe to be slightly more convincing of this, let's go into our y equals. We're going to make this sine x. And then we're going to make our second function, this line that we just came up with, which is, oops, I need to move this up, -x plus pi. And if I hit graph, there's my sine curve. And there's my local linearization at pi. And we can see, just like before, grab my highlighter here, it is a great approximation in that area. Now once I get out of that area, it's not good at all. All right, so here's our next one. This kind of problem, oftentimes students are like, I don't know what I'm supposed to do. So first off, let's understand that when they say show, right here, that means you already know the answer. It means show the work. So show means here's the answer, here's the answer, show the work that gets you there. Show the work that gets that answer. Now, when we look at this, it might not even be clear what's the answer. So when we look at this, the first thing you should recognize right here is this is linear. That means that's my tangent line. And if that side's my tangent line, this side is my f of x. And so all I have to show is that the tangent to this at 1 is this. All right, so here we go. Let's start by naming f of x equals square root of x plus 3. First, we need our point. F of 1 equals square root of 1 plus 3, which is 2. We've got our point. Now we need our derivative. F prime of x equals 1 over 2 root x plus 3. Remember, if you memorize this like I told you to on the handout, it makes the derivative of square root go a lot faster. Derivative of the inside was 1, so I only have a 1 on top. f prime at, and I want this near 1, so I'm plugging in 1 again, 1 over 2 root 1 plus 3. That simplifies to, let's see, square root of 4 is 2. 2 times 2 is 4, 1/4. Feeling good because I see a slope of 1/4 there. I got a slope of 1/4. All right, so now I'm going to change colors. So now we've got y minus, my y coordinate was right here, 2, equals my slope right there, 1/4 x minus 1. Now you might say, hey, I found my tangent line. But until my tangent line looks just like this one, I'm not done. So let's keep going. Y minus 2 equals 1/4 x minus 1/4. Let's add 2. 1/4 x minus 1/4. I'm going to write 2 as 8/4. This is looking good. Equals 1/4 x plus 7/4. And there we go. I have shown that this function is approximately this, because this is my tangent line, when x is equal to 1. All right, one last problem. Tangent line approximation for f of x equals e to the kx when x is near 0. We're going to have extra variables in this, but this does not frighten us at all. All right, so just like before, we need to find our y-coordinate. So e to the k times 0 is going to be e to the 0, which is just 1. So we've got our point. Our point is 0, 1. And then we can do our derivative. F prime of x equals, chain rule, e to the kx, derivative of the inside is k. There we go. So f prime at 0 equals k e to the k times 0. And that's going to just be k. So there's my slope. And here's our tangent line approximation. Y minus 1 equals k x minus 0. And this can, of course, be simplified as kx plus 1. All right, I hope that helps. Get started on your homework assignment, section 3.9, 1 through 6, 9, just parts A and B, 11 and 12.